Kind of a short one today, motion in 2 dimensions. So this is finally, we're getting to the 2-dimension stuff. It's only been 1 dimension really so far. The sprinter in the 100-meter race, the skier going down a slope. We tip the axes sometime to make it a 1-dimension problem rather than 2-dimension. We can represent the displacement, velocity, and acceleration by vectors directed along the single axis of motion. But in 2-dimensional motion, the object moves maybe along a curve in a plane of motion. For example, the skater gliding around a rink moves in a plane defined by the surface of the ice. The rider in a Ferris wheel moves in a vertical plane. Stuff like that. So the object moves in a 2-dimensional motion situation. The displacement, velocity, and acceleration vectors all change and point in a lot of different directions as the motion occurs. So therefore, we cannot just tip the axis and make the motion 1 dimension. We don't have a choice here. It's going to have to be 2 dimensions for sure. So the figure here shows a car slowing down as it approaches a curve. We know that it's slowing down because the vectors are getting shorter. And then it speeds up as it exits the curve, as you should do, as you know, if you drive. So the figure, the first one, A, shows the displacement vector from one point to the next as the car's position changes. And we can see 1-second intervals. And then, because the velocity vector is just the displacement vector again, multiplied by 1 over delta t, the velocity vector points in the same direction as the displacement vector from one point to the next in the same interval of time. So as a result, we can represent the velocity on a motion diagram by the same vectors that extend from one dot to the next, just like the displacement vectors. We already know that anyway. So anyway, we have displacement here and velocity here. Okay? But you see that we're moving in 2 dimensions here. We started off going kind of up, and the other, at the end, we're going to the right. All right, so a kayaker goes over a waterfall. So we have the nice picture that shows that idea, but we paddle over the edge of the waterfall, which means we're going to arc down towards the rest of the river below. It's kind of like the ball going off the ramp problem. So we show the position at 0.1 second intervals here. Estimate the kayaker's velocity during the time interval from 0.5 seconds to 0.6 seconds. All right, so 0.5 seconds is this dot, and 0.6 seconds would be this dot. So how do we estimate the kayaker's velocity if we are looking at the position versus position?
Position versus position.
Right.
So
What do we do?
we would line up the dots with like where they are on the axes. Right?
Okay, sure.
So 0.5 seconds is about 2.5. 6 seconds is about 3.
Okay, so yeah, if I extend this down, try to make it as vertical as I can, and then this one also. This is what you're saying, right?
Yeah.
Okay. And if I do the same over here,
Mm-hmm.
that's pretty close. And then this one over here. There.
So for the 0.5 seconds for going to the y-axis, it would be about 875. And for the 0.6 seconds going to the y-axis, it's about 0.25 or 0.2.
Well, so what we care about is the change.
So subtract them.
How much should we change in position?
Which way?
That's a good question.
In Y, we changed
Yeah.
around 0.7.
Yeah, 0.7 meters a second. And then the other one is about 0.5 meters a second.
So, which way? Let's answer that question first. Which way
It
are we talking about?
decreased Y, increase in X.
Okay, so which way are we talking about? Why not both?
Yeah, it's that curve. Because it's decreasing in the y, but increasing in the x.
So if we're estimating the kayaker's velocity, that's the question, right? Estimate the kayaker's velocity. Where is the velocity vector? You don't know?
The time position.
If I told you to draw the kayaker's velocity vector right now, where would you draw it?
Oh, you draw it
The top
immediately to
right,
the dot.
top left, bottom right there.
Yeah, you draw it between the two dots,
If I connect the dots.
Right there.
Books.
right? That's the distance we're trying to find. The length of that vector.
Shouldn't be so bad.
No. So how do we find that length?
Oh, wait, do we label the?
A triangle,
It is a triangle, yeah.
right there.
Uh-huh.
Uh-huh.
So how are we gonna find that length?
Use the distance on the bottom, distance on the left, and use the Pythagorean theorem.
Yeah. Distance formula, Pythagorean theorem, that's right.
Would we label the length for that
Yep.
on both sides?
So basically you're gonna estimate, because we don't have exact values here. So we need a good estimate for this length right here.
I think that's basically 0.5.
Basically 0.5, okay, we need a good estimate for this length right here.
You wanna do?
It's more than 0.5, it looks like.
It's like, yeah, I was thinking 0.65, 0.7.
0.7, maybe 0.75,
Yeah.
0.775, something like that, okay. So if we said that much,
0.7 squared plus 0.5 squared equals c squared, and then square root it.
okay, what do you get?
Okay, so
75.
yeah, 75. 0.75 squared, and then 0.5 squared. And then the square root. 0.9.
0.9?
Yeah, I don't know how I got that.
What do you mean you don't know how you got that? Did you not do,
I did. I put 0.75 squared
Uh-huh.
plus 0.5 squared
okay,
equals 0.18125, and
Okay.
square root that, I
Yeah.
get 0.9.
great. Okay, so 0.9 meters, that's your delta D, right? So that's the length of the vector right there. So then over delta T. So that's the velocity. Velocity equals delta D over delta T.
So 0.9 meters over 0.1 meter second.
I think so.
Or did we just calculate the length of that vector and that's it?
Well, it says estimate the kayaker's velocity, so we'd have to put it into like something per second.
Okay,
So we could just take the 0.9 and times it by 10, and we get 9 meters a second. Because it's going from 0.1 seconds to 1 second.
Why not just put 0.9 meters over 0.1 seconds?
0.1 seconds?
Because that was the interval, no?
Yeah, the interval's about a tenth of a second each, right?
Yeah.
So 0.9 meters divided by 0.1 seconds. What do we got?
Do we want to use the previous answer? Or 0.9?
Whatever I mean, divide by 0.1, we're just moving the decimal
Yeah. it's
one
just
spot, right? Okay, so what do we got?
9.01.
So 9 meters per second then. So based on our estimates here, I don't know if this is right or not, but this is what we said today, that he's falling now at a rate of 9 meters per second in the direction of this vector, okay? He's not falling straight down, he's not falling forward, he's falling in the direction of this vector, okay? So that's how you do two-dimensional motion problems. We have a down component, we have a forward component. We needed to put those together before we were able to answer the question. Make sense?
Yeah.
Okay, good. All right, so now finding the acceleration vector. This is kind of an interesting thing also. to find the acceleration as the velocity changes from the initial velocity to the final velocity. So what we can do is we can draw the final velocity vector. So this is important. It's the final velocity vector that we're talking about here. Then we draw the negative initial velocity vector. So we had the final velocity vector here. Okay, that's what we're doing right now, final velocity vector here. Now the initial velocity vector here, reverse it and put it at the end of the final velocity vector. So now that is drawn here. The acceleration vector that pulls the final velocity vector in the direction that it's going is this guy that would give us the resultant if I added those two vectors together. That is your acceleration vector right there. Okay? So it might not be the right magnitude, but it is the right direction of the acceleration vector. So that's it. That's how you would find your acceleration vector. So now back in this problem, or in this drawing right here, we have our initial velocity drawn correctly, our final velocity drawn correctly, and then this acceleration vector that we just drew by making that reversed initial velocity vector and putting it at the end of the final velocity vector, that acceleration vector is drawn in the correct direction.
No matter what?
Every time.
Okay.
Okay? It's kind of an interesting way to figure out which way the acceleration is going if you have the two initial and final velocity vectors.
So delta V is acceleration.
No.
Oh, then.
Okay, well, sure. Yeah, you could say that. In this, the way that they have this drawn, yeah.
Okay.
But what's really going on here is we have our acceleration vector then, okay? So, skiing through a valley. So we have all these words here, but what it boils down to is this. The skier is skiing down a long straight hill, so that's this first portion right here through this segment here, okay? Long straight hill. Then we go through the valley. So the valley is this curved portion, and then we have another like long straight uphill that the skier is somehow going to be able to go through, okay? So they don't run out of speed completely on the other side. So we see that since this is a long straight valley, what is happening to the velocity, the green vectors?
They're getting longer and longer.
So we see that the skier is speeding up, right? And we go through the valley, let's talk about that in a minute. But on the other side, we have this region right here. What's happening here?
Slowing down.
Slowing down.
Because of gravity. So wait, why are the middle yellow ones towards like the center of it?
So we'll talk about that in a second. What's happening with the acceleration as we're speeding up?
It's getting.
What? Tell me about the acceleration only.
Acceleration is not constant.
It is
Is it
constant.
constant?
Yep. So constant acceleration. That's because gravity is pulling straight towards the
yeah.
center of Earth. The hill is a constant angle, so therefore the acceleration is constant. What about the acceleration in the slowing down phase? Also constant acceleration. It's a angle on the hill that is not changing, therefore the acceleration vector is not changing either. So acceleration is constant here too. Now, what's happening in the middle?
It's constant velocity.
Is it constant velocity?
It looks like.
No. The answer is no here. Even if the speed does not change, the velocity is not constant. How come?
Because it changes because it goes more steeper.
Yep, because the direction is changing. Okay, remember velocity requires magnitude, which is speed,
Same direction.
and also direction. Okay, and the direction is definitely changing here, therefore this is not constant velocity.
So it's
All
just
right?
constant speed.
So maybe constant speed, we don't know, but definitely not constant velocity.
Yeah.
Okay? So first let's look, well actually what I want to look at here is the direction of the acceleration. Okay? How do we calculate the direction of the acceleration again? We take the velocity final. Okay? So let's just look at velocity final. So here I'll take a velocity final vector, and then I'm going to take the previous initial velocity vector. So my previous initial velocity vector is this guy right here. I'm going to reverse its direction. So I reverse the direction. Okay.
Oh, I see it.
Now I'm going to pick it up, and I'm going to place it with exactly the same magnitude and direction that it currently has. Okay? Now, tip to tail would be this right here. Okay? So that's the direction of my acceleration vector. Like I said, I don't know what the magnitude of my acceleration vector is, but I do have the direction correct. All right? And if we continue to do that all the way around, for example, this one. Here's my final velocity vector. This is the result of some sort of acceleration that I don't know. I take my previous initial velocity vector, reverse its direction, pick it up, and lay it down tip to tail on my final velocity vector. And now I have the acceleration vector that caused me to turn. I don't have the magnitude of it, but I do have the reason why I turned. It was due to that green acceleration vector at the end of my initial velocity vector. Okay? So that's how we end up turning every single time. Okay? Now, obviously the drawing here is giving me these longer acceleration vectors, and that's fine. I didn't know how much acceleration I had to make me turn, but I do know the direction that it was. Okay?
Wait, then. Okay.
So yeah, when you draw a motion diagram, remember that the motion diagram has to include the dots at regular intervals, which we have, the velocity vectors, which we have, and also where is the acceleration? What's the acceleration doing along the way? In this case, the acceleration is pointing down the hill. And then how did you calculate in the curve? Okay, so you wouldn't draw these vectors that I'm drawing now, like those would not be there. But those acceleration vectors would be there. And then still down the hill on the way back, as we go up the hill, the velocity is going up the hill, but it's getting shorter and shorter. And then the acceleration, though, is pulling us down the hill, okay? So the motion diagram is here. We've already drawn it, but now I'm explaining how it got drawn, okay? All right, good. So that's the whole problem there. All right, so almost done now. The positions of 4 cars on 4 different roads are indicated by the dots. Which cars could possibly have the acceleration vector that's shown?
I feel like it'd be C.
You could have more than one answer.
And
B. Wait.
I feel like that'd only be it.
Which cars? It's plural. A, B.
Could C have that acceleration?
Yeah.
Yeah, it's going down a straight road. It could be accelerating and moving which way? Left. It could be moving to the right, maybe, and having that acceleration. Is that possible? Would it be speeding up or slowing down?
Speeding up.
Speeding up, moving to the,
Left.
or moving to the right and
Slowing down.
slowing down. Yeah, so C is definitely a possibility. What about any of the curved ones?
I don't think it'd be really anything with D, because
It's to
honestly,
the right, and it's not slowing down because it has that curve at the bottom. Or would it be slowing down?
what does it mean by the position? Is it just like a turn in a road, or?
So the cars are in the A, B, C, D spots right now.
A.
And the lines
Because
are
if they
like,
move down, they can, like, it's after the curve and they start speeding up. No?
No.
so the line is like the curve of the road.
Yeah, the line is the curve of the road, yeah.
I feel like it wouldn't really be much with D. So I
Why
feel
not?
like because it's going
Going
both
opposite
different, yeah, both opposite ways.
What do you mean by opposite ways?
It's going opposite of the
Oh, yeah.
acceleration.
You can see that A is going.
We can't accelerate that way?
Wasn't
No,
the
there's no
acceleration
road.
going that way?
Yeah.
Then why are you going that way?
Yeah. That's right. That's right.
Okay.
No, you're right. What about B?
Uh,
I feel like it would only be reasonable if you're going down that way.
Okay, so what direction should the acceleration vector be pointed if we're in B right now?
Like
Left.
south of east or west.
What, south?
South of west.
South of west?
Straight down?
No, how
So
is
it'd be
that?
pointed this
South
way?
west.
Your velocity could be pointed that way. Could the acceleration?
No. Wait.
Which way should it be pointed?
Left.
No.
Down?
Let's go back for a second.
I'm good.
Look at the curve here. I intentionally did not talk about this. Which way is the acceleration pointed every time in the
Inside,
curve?
so it's only A.
It's always inside, but more importantly, they're all kind of pointed at something. Can you see it?
The center of the.
The center of the curve. There is a curve here,
Oh, is that 'cause, like, since-
and they're all pointed pretty much at the center of the curve. Yeah. So in B, where would this vector be pointed? Yep, it would be pointed more like this. It's not B.
Okay,
And
so
where
it's
should the vector for D be pointed?
that way.
The other way.
Ah,
So it's
A,
not
C.
D. But A could be, for sure,
So it
right?
could be A and C.
So definitely C
Maybe A.
and maybe A. If we're driving at all, right?
Why am I always right on these problems?
Okay, so there you go, done.